Hello, in this video, we're going to be talking about the fundamental theorem of calculus, trying to bridge our gap between our derivatives and antiderivatives. Cut right to it, here we go. If a function is continuous on a closed interval and f is the antiderivative on that interval, if we have this definite integral, we would be able to figure out the definite integral by just doing the antiderivative of f at b and then subtracting the antiderivative of f at a. And so we can write that out as this, where we kind of write our antiderivative. We got b and a, and we kind of subtract our top value minus our bottom value. Whatever is on the top of that definite integral minus whatever is on the bottom of our definite integral. Now, how we actually find that antiderivative is not going to be covered in this video. What we're going to be concerned mostly about is this one down here, our second fundamental theorem of calculus, which states that if we do the derivative of an antiderivative, these two operations are kind of inverses of each other, but they do cancel each other out. So we're left with just our f of x. One thing to note, though, is that note that here f is defined by t, but then this x value kind of plops its way into our function and replaces that t with an x. Let's see that in action. So I want to find the derivative. So I want to find the derivative of this thing. All I need to do in order to figure out what the derivative is just drop this x right in here. That's what our second fundamental theorem of calculus is. We get tan cubed of x. And then we're just kind of done. That x value is able to just plop its way right in. We don't actually have to do anything with this tangent. We don't have to find its antiderivative because would find the antiderivative. That's something I don't know right now. But then I would just find the derivative of it anyway. So I antiderive and then derivative. So why don't I just skip that back and forth and just write the original function? Now note, it doesn't matter what this number is down here. We'll take a look at y in our next example. Here we, again, are going to try to find our derivative. So I would just drop that x squared into our function. So we would get the cotangent of 3 times x squared, just replacing that t with our x squared. But we're finding a derivative of this function, but inside of that function, we've got another function. So we do have a little bit of extra work. We have to figure out what the derivative of what is inside of there, doing a chain rule. So the derivative of x squared is going to be 2x. Now, what about that 6? Let's think back to the fundamental theorem saying that we want to do whatever is on the top minus whatever is on the bottom. So let's actually do that this time and subtract what is on the bottom. So we would subtract doing that same trick with this number on the bottom. So that would be cotangent of 3 times 6, just plugging in that 6 where that t was. Again, I'm not changing cotangent because I'm basically being asked to find the antiderivative of it and then find the derivative of it again. Really done nothing if I antiderive and derive. But then I want a chain rule just like I did up above. So I need to figure out what is the derivative of 6. Oh, our derivative of 6 is just 0. So this would be 0 times the cotangent of 3 times 6, which is just 0. So that's why it doesn't matter what number is on the bottom. When we would apply a chain rule to it, we would just end up with 0. So this just equals that first bit, making sure we apply that chain rule. Now that trick can be done if we have x's in both of those spots. We just need to actually remember kind of the lesson we got from the previous example, that we need to do the top minus the bottom and subtract those two values, making sure we apply our chain rules where appropriate. So to find the derivative of this thing, I would plug this x cubed right into here. So I get the cosine of 2 times x cubed, but then I would have to chain rule off of that, finding the derivative of what was our inside function being that 3, our x cubed, which will become 3x squared. Now, by the fundamental theorem of calculus, I have to do whatever's on the top minus whatever is on the bottom. And I'm not going to be so fortunate to get 0 this time because we've got that x squared this time. So that x squared is going to take t's spot. So we get cosine of 2x squared. Again, I'm not doing anything to that cosine because I would find its antiderivative and then its derivative. I've really done nothing, so I can just leave it as that cosine. And then I've got to chain rule and figure out what the derivative of that x squared is. That is going to be 2x. So this is the derivative of that antiderivative, applying the first and second fundamental theorem of calculus. Now we can get a little bit more creative with this and just let g be a function defined by the antiderivative of f. So this is one function separate from g. We have the graph of f over here, and we want to know what is going on with g. Now, because we've defined this as a function, we can treat this as a function. We're asked to estimate g of 0. Well, just like a regular function, if I was asked to find g of 0, that means replace this x with a 0. So this would be the antiderivative from 0 to 0 of f of t. I'm going to keep that as a t because right here that is x, not t. So just leave it like that. Now, what is the antiderivative from 0 to 0? So that is the area underneath the curve of a line. Well, a line has no area, so this thing is going to equal just 0. If we were trying to find g of 2, that would be the antiderivative from 0 to 2 of f of t dt. So that's asking us what is the area inside of here from between 0 and 2. I've got a rectangle right here. That area is 4, and then I've got this trapezoid. I've done the work of the trapezoid off to the side. I found its area to be 3. So that has a rough area of 7. I'm going to skip to g of 8, and I want to find the area underneath this curve from 0 to 8. So we know this area over here is 7. We could find the area of this triangle. That's going to be 2. And then there is a negative triangle down here because now we've crossed below the x-axis as opposed to everything that we were finding before was above our x-axis. Since this is going to be negative, its area is going to be -4, just finding that area of the triangle. So g of 8, which is f of t dt from 0 to 8, is going to have an area of 5, 9 minus 4. In part B, we're looking for open intervals where g is increasing and decreasing. I know increasing and decreasing is talking about the derivative of the function. So I need to figure out what is g prime. Well, that's just going to be the derivative of the antiderivative from 0 to x of f of t dt. Okay, well, the antiderivative of derivative of an antiderivative is just going to undo each other. So g prime of x is going to be the same as f of x. So in order to figure out where g is increasing and decreasing, I need to know where g prime is positive or negative, meaning I need to know when f is positive or negative. So I'd make a sign chart. I see one spot where f equals 0. F equals 0 right here at 4. That is going to be my critical value for g prime since f equals 0 and f is g prime. So if I check values over here that are less than 4, I can see that f is positive, meaning g prime is positive, meaning that g is increasing. So g prime is positive, so g is increasing. And then after 4, f is negative, so g prime is negative, and g is decreasing. So we could write out our intervals now. Note that this problem was not asking us to justify, so I didn't need to write what's here in red, but I just put it here in case you wanted to visually see what I was saying rather than just trying to get it off of the words that were coming out of my mouth. But G is increasing from 0 to 4, and G is decreasing on 4 to 8. I chose to use open intervals because they asked for open intervals. So open intervals is what you're going to get. In part C, I need to identify any extrema for G. At 4, I've got a maximum since G prime is shifting from positive to negative at that point. I'm also thinking about endpoints when we're talking about extrema, because we can have extremas at those endpoints. However, it's not very clear in the book or in this problem whether these are endpoints of F, and if they're endpoints for F, they're probably endpoints of G, but that's not very clear based on how the question is written. In the back, they're only looking for this one. If we were to include it, we would still do our regular thing based on the first derivative test, that since we're increasing after this point, we would have a minimum at 0, at x equals 0, and we would have a minimum here as well at x equals 8, since we're decreasing into that point, all based on the first derivative test. That is it for our video on the fundamental theorem of calculus. A reminder that if you do the derivative of an antiderivative, that these two operations just sort of undo each other, and we're left with just our original function. Doesn't matter what this number is. If you got a number there, it just is gone. Can be whatever number you want, don't matter. However, if we do have other things going on here where that x is, you need to apply a chain rule, because that's a function inside of a function that you're trying to find the derivative of, so be sure to chain rule that thing out. This can be applied in lots of cool ways, as we saw with that first derivative test. Second derivative test could come into play too. All that good stuff. Thanks for watching, and I'll see you next time. Bye-bye.